Okay, so I'm using the chapter for this portion as well. I'm going to do, I think, the next two sections at once. One reason that I'm using this is because then I don't have to reproduce graphs. Another one is um, that it's still pretty conceptual at this stage. And also, I think if you try to look through this example, the way it's written, that most of you will find it quite confusing. So I'm going to go through it and kind of explain what's happening. So what we want to look at is what happens if more than one sample is taken from a population. So sampling distribution is what we've used all along, like when you graph the results of something, then it was called a distribution. When you graph the probabilities of something or list the probabilities, it's called a probability distribution. The normal curve is the normal distribution. So distribution is just kind of how things are laid out. So the sample distribution is the distribution of the means of the sample or the percentages of the sample or whatever the result is that you're after. So we're going to focus on samples where we're averaging. So we're looking for the moment, so we're looking for the average of something in the population, and we're basing it on samples and multiple samples, so that we're going to look at then the means of all the samples. So like when you do your Cheeto lab, you will each have something that you can average. So each of you will have a sample of, I think, 3 Cheetos, each group, and each group will be able to average that, and so then we'll have a list of averages from each of the different groups. Okay, so we're going to pretend for a moment that we have God perspective and we actually know the whole population. And we're actually going to, for the moment, assume that there are only 10 people in the population. For whatever reason, we still want to do sampling. These are all, of course, mixed up. So what we're looking at is the average of how much money people had in their pocket. And this is our whole population. And so it looks more interesting than it is, because if you analyze it, you've got $0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's actually just all the numbers from 0 to 9. There are 10 people, and if you average that, you'll find that the average amount of money they have is $4.50. But we're assuming we don't know that, and that we have 10 different people to start with who are going to do samples of size 1. And they're each doing different samples. So basically, one guy has this guy as his sample, one guy has this guy as his sample, one guy has this guy. So the result, the averages from each of the samples are going to be 0, 1, 2, 3, because it's just the one guy. So your average is whatever they had. So that distribution then looks like this. There's a sample, sample mean, sample mean, sample mean, but it's really just each guy, right? Okay, so then we're going to say, suppose instead that we're going to take all possible samples of size 2. All possible samples of size 1, there are 10 of them, because there's pick the first guy, pick the second guy, those are all the possibilities. So you have 10 possible samples. Once you go up to size 2, though, you increase the number of samples by a pretty good amount. And the way you find out how many samples of that size there are is you have 10 ways to choose your first person. You have 9 ways to choose your second person, but choosing A, B, and choosing B, A, these are the same sample. And every single combination has been counted that many times. So you divide by 2 so that you don't count everybody twice, and you get 45 ways to have a sample of size 2. So when we graph that distribution, we're going to have now 45 dots instead of 10. Some of them will be the same sample size, sample mean, because now you might have chosen 0 and 8, that has an average of 4. You might have chosen 1 and 7, which also has an average of 4. 2 and 6 also has an average of 4. 3 and 5 also has an average of 4. So you'll have multiple values that have an average of 4 this time. So you'll have dots stacked on top of each other. But there's only one sample that gives you an average of 1. It's the 0, 2 sample. That dot should really be here on a half. This plot isn't quite perfect, but it's close, so you can get the idea. The ones I listed with an average of size 4 are kind of not above 4, but should be 4 and a half. Could be the result of 4 and 5, 3 and 6, 2 and 7, 1 and 8. Those all have an average of 4 and a half. Oh, and 0 and 9. So there actually should be 5 here. So you start to get, as you increase sample size, you start to have where more and more are kind of getting closer to the real average. But something else is happening as well. So now we're going to move to a sample size of 3, which then is similar to this. You have 10 choices for the first one, 9 choices for the second one, 8 for the third. But this time you have all these ways. And you may not be confident that you've gotten them all, so you wouldn't necessarily just divide by 6, right? And especially as we get larger sample size, this would get more confusing. So the way that you do it, and this is just a button in your calculator, but back in the old days we did it by hand, and it was pretty fun, I thought. But anyway, so 10 times 9 times 8 divided by, once I have a particular sample in mind, because I want to know how many ways did I count each of these samples. There are 3 ways. I might have chosen the first. I could have chosen A, B, or C. Once that was selected, there were 2 ways to choose the second one, and then 1. So this is how you calculate the number of ways to choose 3. So that's how many dots you have, 120 dots now. So you have many more copies of each possible combination. One thing to note is that on this one, you only had dots over whole numbers. Here you had them over halves and wholes because you were dividing by 2. Here it's over 1/3, over 2/3, or wholes. 1/4, 2/4, 3/4, and wholes. There are 210 ways to have 4. And this is what the distribution looks like. Here's 5. So remember, every one of these is a sample mean. So now the lowest mean you can have is 2, because if you choose 0, 1, 2, 3, 4, the average is 2. And there's only one way to do that. Same thing up here with 7, I assume that's supposed to be. And then here's with sample size 6. Now you can't get 2, right? So it's all kind of squishing together because you're having less and less chance for outliers to mess you totally up. So the more that you choose, the closer you get to having the average be the average, but also the closer you get to it being actually normal. So it turns out that the distribution of sample means is approximately normal. So no matter how crazy skewed or uniform or totally scattered around or whatever your individual values are, so if the number of dollars that people have in their pocket is actually wildly not normal, if you take a bunch of samples and you only plot their means, that actually is normal, no matter what that's normal. So we can use then rules about normal distribution to analyze these sample means and what they mean for the population mean, what they indicate, I guess I ought to say. Okay, so this is my third time attempting to record this because it keeps being unable to record and I don't realize it until I think I'm finished. So I may repeat myself and hopefully I won't leave anything out. But okay, so um, I think I already told you that no matter how crazy your actual samples distribution, if you then average all of them and instead look at the distribution of those averages, then that is approximately normal. It's really approximately normal at sample size 30 or greater, but you can kind of use it. You can see here, even with the size 3, it was, not horrible. Size 4 is quite a bit more normal, but um, at any rate, I think your Cheeto Lab has a size 3, and we're going to use it. So it won't be perfect, but we're going to use it there anyway. So what happens is that you have, as you increase the sample size, it gets more and more and more and more normal, and you can calculate what we call a standard error. So if you're just looking at a list of values, and you just look at that and you don't look at averages or percentages or anything else like that, it's called a standard deviation. So that's a list of particular people's results. Then you call it a standard deviation. If it's anything else, you call it standard error. So we're looking for the standard error of the sampling distribution, of the sample means. But it works just like a standard deviation. So it's just a different name. So once it's normal, then you get these values that you would get from the normal curve. So we can say, well, 95% of the samples fall within 2 standard errors of the sample mean. So if you take a sample of size 30 or better, you can say, I'm 95% sure that the mean of my sample is within 2 standard errors of the actual sample mean. And the way you calculate the sample mean standard error is by taking the standard deviation of actually the population and dividing by the square root of n. Where is that? Oh, it's down here. So as n increases, that gets smaller. And you can see, like up here, we were still able to get an average of size 2 because we had the 0, 1, 2, 3, 4 sample. But here we couldn't. It had to be up nearer 2.5. The more you do, the harder it is to get an outlying value. So you get closer and closer to this sample mean, to the population mean with your sample means as you increase size. Okay, I'm going to pause and save. Okay, so the central limit theorem says as you increase the sample size, the closer to normal the distribution of the sample means gets. So the more people per sample, the more it looks like a normal distribution when you plot all the means. So this is a little review of just notation. And basically what happens if it's normal, you know that there will be a mean of the means. So if all my plots are means, then on a normal distribution, this middle bit here is the mean of those means because it's symmetric, and it will be also the true mean. So the average of the sample means is the same as the average of the population. Okay. So you can take from the population in the sample if you know about the population. So essentially, if you know the population standard deviation for that value, so in this case, the standard deviation of those 10 people's money, then you divide that by the square root of n, and that's the standard error for your sample means. So you would, if you knew the standard deviation there, you divide by the square root of 30 if you have 30 samples, and then you're dividing by more than 5. So it's getting, a lot closer. Your means are a lot closer to the mean than any given value would have been. And then once you have that error, you can say, well, I'm 95% certain. Let's say that the result of this was 2. You could say, well, 2 standard errors then is 4. So I'm 95% sure I'm within 4, that my mean is within 4 of the true mean, which also means that the true mean, indicates that the true mean is within 4 of you with 95% certainty. So then you can put an interval around yours. So if your mean was, say, 500, then you could say, well, I'm 95% sure that the true mean is between 496 and 504. And that's the confidence intervals that we'll get to later. It's just adding and subtracting the right number of standard errors to ensure to some stated certainty that you have captured the true mean within this interval. So here's an example. The time it takes a student to complete the midterm for Algebra 2 is a bimodal distribution with mu equals 1 and sigma equals 1. Wow. During the month of June, Professor Spence administers the test 64 times. What is the probability that the average midterm completion time exceeds 48 minutes? Okay, so we're going to expect the average midterm completion time to be 1, because that's mu, and our standard error for samples of size 64 is going to be 1 divided by the square root of 64. Pause and save. Okay, I had previously done the third example instead, so clear. Sorry about that. Okay, so we have mu and sigma are 1, and 64 is the sample size, and we want to know the probability that his mean was greater than 48 minutes. So I guess really, since we're in minutes, mu is 60 and sigma is 60 because we want to have all the same scale. So the mean of the means of size 64 sample will be 60. And here's 48, and we want to know this part. So the standard error for the sample means is going to be the standard deviation divided by the square root of the sample size. Okay, so our z-score is 48 minus 60 over 7.5. I may want to change that back to 15 halves. So negative 12 over 15 halves is negative 24 over 15, negative 8/5. Okay, so negative 1.6 is our z-score. Negative 1.6. 0 gives 0.0548 to the left. Which leaves over here 1 minus 0.0548. So I think they're changing it to percentages they did on the other example. So 94.52%. Okay, now I'm going to actually, well, you pause here, and I'm about to pause also and save. So you see if you can do this example. Okay, so here's the solution for that one. Now you check yourself here, and then try this one. Okay, now here's that solution. That's the one I did last time. I'm going to let you read these and kind of pause, make sure you're clear on that. And then the next section is confidence interval. And having recorded this particular video so many times due to Camtasia issues, I don't have time to do a video on that before this afternoon. So there's seminars on it this afternoon. And then I will post the video this weekend at any rate.